I've come here from DOGAMI to present to you on geologic carbon storage potential in Oregon. It's a big topic for DOGAMI at the moment. I'll come on to that in a bit. I thought I'd take you through a few different aspects here as a sort of a who, what, why, where, and how, just to make sure that everyone's on the same page. What is geologic carbon storage and CCUS as well? Why do we need it? Where are we investigating, and how does Oregon actually fit in? And I'll start the why with the who with who I am. Martin gave me a nice introduction, but a lot of my career to this point has been in the natural systems of fluid and rock interactions in basaltic and ultramafic rocks. So well placed in a state like Oregon to come in to try to better understand the natural system, but also in systems where we're going to be potentially inducing some of those capitalizing on some of those natural systems. So I've spent a lot of time working in the growth of faults and fractures in basaltic provinces, largely in the Faroe Islands, North Atlantic margin, Greenland, but then also in volcanic edifices around, largely in Europe, but also Hawaii. And so, as I say, this sets me up nicely for Oregon. I guess in a bit you might see this as foreshadowing for some of the topics that I'm going to be talking about with respect to carbon storage. Before I go on, I do just want to say, so I'm the Decarbonization Geoscience Lead at DOGAMI. It's a new position that was created last year. That was associated, well, that position is associated with a large project that we have through the state to investigate geologic carbon storage, but it covers carbon storage, hydrogen, critical minerals, and geothermal energy. And we've initiated a new subsurface geology mapping program. A lot of the work that we've been doing so far is surface-based, but we recognize that there isn't a huge amount of subsurface data for the state of Oregon, and we need to expand that. With that in mind, so I have put out, and we've got some of these flyers that we've put together. Now, they're not aimed at university undergraduates, graduates, and faculty. They're really aimed at broad interest, but you're welcome to take those. There might be enough, and if there aren't, and people want some of these, then we can provide them afterwards. So, start really with what it is. So there are a couple of terms that get used quite a bit. Starting to realize the text has not transferred that well, but a couple of terms that we need to make sure everybody understands. CCUS, which is a term that's used a lot, carbon capture, utilization, and storage, sometimes referred to as sequestration, but the sequestration really just means the process of capturing it, utilizing it, or storing it. And then I'll be talking about GCS, that's the geologic carbon storage, and that is very specifically the process of putting it somewhere underground or on the surface using geologic processes. So GCS, a component of CCUS including things like direct air capture, point source capture of CO2. I'm really going to be focusing on the GCS component because as a geologist, that's where I sit really. And before I really go any further, I think it's important as a scientist to actually explain why we're interested in doing this or why there might be a need for it before moving on to the fact that we're going to go ahead and start to look into some of these things. And I don't think I really need to spend too much time preaching to you about the need for geologic carbon storage. We are in a climate crisis. We have been excessively producing CO2 and other greenhouse gases in such abundance that we have affected the atmospheric concentrations. So since industrial times, we've increased CO2 concentration from around 300 parts per million up to 425 parts per million. That is having a massive impact then on global climate. And really it comes down to these numbers on the right-hand side, the emissions, the volume of the emissions that we have. 40 billion tons of CO2 being emitted from anthropogenic sources in the present day. Compare that against around about 100 million tons produced by volcanoes globally. So it's wildly in excess of natural cycles. We can see that if we take the rock record, or the ice record, I should say, back to 800,000 years, we have never seen so much CO2 in the atmosphere, at least not for several hundreds of thousands of years. So a bit of context then. As I say, that CO2 is causing climate change. It's causing global warming, and we've seen so far since pre-industrial times about 1.3 degrees Celsius increase in global temperature. There are targets to stop us exceeding 2 degrees C with the Paris Climate Agreement. The original target was 1.5 degrees, but they changed that because there's no chance of us meeting it. By taking the target and what we know we've emitted so far, we can estimate that it's actually going to be about 800 billion tons, or gigatons, as it says there, before we hit 2 degrees. And if we take that 40 billion tons per year of emissions, then we have around about 20 years to get rid of, or to stop emitting so much CO2. For context, though, the human population weighs on the order of about 500 million tons, and we produce about cumulatively 2 billion tons per year in solid waste. Contrast that against the 40 billion tons of CO2 that we're emitting, CO2 equivalent. That's the scale that we're really talking about. What happens to that CO2? Well, it goes into the atmosphere, and ultimately, if we don't do anything, it's going to cycle through the atmosphere in a matter of years to decades, and it's going to end up in the ocean. Currently, around about 25% of CO2 in the system that is emitted is arriving back in the ocean. That's causing ocean acidification, but it's also, I think, something like 90% of the heat increases being taken up by the oceans as well. So it's a pretty dire situation if we don't do anything. That's globally. We're not, although we're a green state, we're not entirely green. Oregon emits around about 60 million tons a year of CO2. For context and comparison, there have been studies that estimate the amount of CO2 that's taken up by Oregon's forests, and on an annual basis, they're responsible for taking out about 30 million tons. So we still have an excess of production of CO2 above what the natural system can take up. Still doesn't answer, do we need carbon storage or geologic carbon storage? And the answer is still yes. CCUS contains the U, which is the utilization. Could we just use that CO2 for other purposes? Maybe, if we weren't producing so much of it, but currently we're only utilizing around about 230 million metric tons. So that's about 0.6% of what we're emitting. And it gets a little bit worse than that, because the vast majority of that is being used for processes that also create then CO2. So 80 million metric tons being used for enhanced oil recovery, 130 for agriculture, but a lot of that is then cycled back into the atmosphere. So it's not utilization to suck things out, it's utilization to enhance energy production, food production. Now, there are a whole other range of different uses for CO2, but they're in very small quantities besides those two end products. And there's a great visualization of this by Leclerc from 2024, the carbon dioxide tree, and it's a great study to go and actually have a look at all the places that's being used, but we're never going to get to the point where we need 40 billion tons each year. So that's the sort of introduction of, do we actually need what I'm talking about here? And hopefully you see that we do. So what are the actual options for geologic carbon storage? And there are quite a few different approaches that we can take. Some of the things that are going to be most important in this are what I would say is this, or describe as demonstrating permanence for that CO2, because the last thing that we actually want is to capture it using something like direct air capture, which is a very inefficient process. It's a very energy intensive process. To then take that CO2, put it into the ground with all the energy that takes up, only to find that isn't then locked away for a geologic period of time. Now, to get paid for any carbon storage, whether it's geologic or from land use change, growing forests, changing the way that you use your land, you need to be able to demonstrate that you're locking that CO2 away relatively permanently. So in the compliance market, which is governments issuing credits, generally it's a 100-year minimum demonstration. So you need to be able to demonstrate that your CO2 is locked away for 100 years to be paid that. If you're using the voluntary market, it depends which standard you're using, which group you're using, who's paying the credits, but it's generally still on the order of 20 to 100 years. So it's multi-generational permanence that we're talking about here, and being able to demonstrate it. So whatever we do for geologic carbon storage, it has to be long-term. And to me, the only mechanism of storage is that can guarantee that permanence is geologic storage. So the options, 4 different types. There are multiple ones, but you could probably summarize them into reasonably 3 different groups. On the left-hand side, and to some extent in the middle, we've got the enhanced oil recovery mechanism. So this is using former oil or gas traps, pumping the CO2 into those hydrocarbons to reduce the viscosity of it so that you can get more of it out, and then relying on the presence of that trap to keep that CO2 in that system. There are saline aquifers in those same systems. You can pump into those if you know that it is going to stay there. We also have options with coal systems that you can pump into coal seams that are unminable. Maybe they're too deep. That will also then displace some of the methane that comes out of that coal. So again, another mechanism for generating energy, but yeah, sorry, methane displacement through coal. And then the third one would be to look at injecting it into directly into rocks to react with those rock systems to then create a mineral precipitate. And that's largely what I'm going to focus on, because I think that's where our lowest hanging fruit is in a place like Oregon. I will touch on the saline aquifers as well, because we do have those. So the distribution across the US for those different types of system, you can see that the vast majority of the saline aquifers, that's the SAWs, in the US are in places that are historically associated with oil and gas production: Texas, Southeast, Central, and Midwest US. And then not a whole lot in the Pacific Northwest, largely because Oregon hasn't had an oil industry. There is a bit of a gas industry in the Misgas field, and then going up into Washington. But it's never been a huge market. It's never been a huge system. They are already injecting CO2 into a number of saline aquifers. Again, largely these are in well-characterized, no pun intended, former oil and gas fields, where they can monitor that CO2 or the CO2 plume that results. They can monitor transit through the system, where that CO2 is actually going. But again, not a whole lot over in the west. This map's now out of date because there is some stuff going on in Central Basin in California. If we zoom into Oregon, we do have a number of saline aquifers, but the biggest holdup for us, I would say, is that largely those saline aquifers have not been characterized because they're at greater depth than the usable water that we do rely on. We haven't had that oil or gas industry in anywhere except the northwest, the mist gas field up in the Astoria, Nehalem, if that's how you pronounce it, basin. But everywhere else, largely wells are very shallow. They don't generally target those saline aquifers. And that poses a bit of a problem, like I say, because the key here for GCS is being able to demonstrate permanence. Pumping into any of these systems, largely that CO2 is going to remain in a gas or fluid phase. So the diagram on the right-hand side shows time from injection into, say, a siliciclastic system, and the amount of which trapping mechanism would be responsible for holding that back. The vast majority is going to be reliant on structural or stratigraphic trapping. That's keeping it in its buoyant phase, the same way that oil and gas would be held back largely, but we haven't characterized those structural traps across the state. There are other trapping mechanisms, whether it's held up in pore space or held within the distributed within solution as solubility trapping, but largely it's all going to stay in its gas or fluid phase, in which case you've got to monitor it for upwards of 100 years. So there's a very large toll for future generations if this is a route that we go. You'll see that there is mineral trapping. You will get some mineral trapping, but it's not going to account for the vast majority of injected CO2, and it's going to take on the order of 100+ years before it starts to become trapped through mineralization anyway. So that kind of leads then into the other options for CO2 storage, and using mineral carbonation is probably our best bet, at least in the short term. And you can see from the map, a nicely put together map from Madeline Blonders at the US, when she was at the USGS, showing a distribution of the basaltic and ultramafic rocks. And those are our two best targets. I'll come on to why in a moment. But the Pacific Northwest has a lot of opportunity in those two rock types, whether it's because of the grand surface aerial coverage of basaltic systems or the reactivity and depth component of the ultramafic systems, shown in the orange. Mineral carbonation is a well-tested system. There are a couple of examples that I can point to demonstrate the viability of mineral carbonation in action. So the probably best known one and longest lived one is the Carfix project in Iceland, which is currently the only commercial scale injection of CO2. They've been operating and initiated a pilot study about 15 years ago now, pumping into basalts co-located with one of the geothermal plants. And in fact, that's just here. So the Carfix project in the Hengel Rift system, co-located with a geothermal plant. I wanted to put this up here because there has been talk about, does this cause earthquakes and does it cause volcanic eruptions? The most recent phases of volcanic eruptions are a couple of rift systems separated from that injection, so probably not. But Carfix has been working continuously to demonstrate the viability here. So in their pilot study, they were able to inject 200 tons of CO2 in an aqueous phase. So this is a dilute solution, generally on the order of about 1 part CO2 to 25 to 30 parts water. And what they found from monitoring wells and re-drilling is that what they've pumped and isotopic signatures of the CO2 that was going in versus natural systems, they've been able to see that actually around about 95% of what they pumped in was mineralized within the first 2 years of that injection. So it's a very rapid mineralization that then cuts down on that long-term monitoring that would be required. You can demonstrate permanence because it's then a rock. As I say, that the Carfix technology is what we could refer to as a sparkling water. It's the Perrier approach. And the proprietary nature of what Carfix do is that they've worked, as I say, for about 10 or 15 years on what those compositions need to be, what the fluid compositions can be for rapid mineralization, how much CO2, and the best way and time to pump CO2 into that water, or to mix that system would be. Because of the geothermal gradient for Iceland, it's a bit higher than it is around here. They're injecting around 400 to 800 meters, and the system works very well. As I say, it's within 2 years, what they've pumped in is generally, well, in the vast majority, has then crystallized into a carbonate mineral. And so far, over that period, they've pumped in over 100,000 tons. They're aiming for 3 million metric tons by 2031. So it is ramping up, but I would say the main holdup at the moment is access to consistent CO2 supply rather than actually the viability of the injection system. There have been studies closer to home. So the Wallula Basalt Pilot Project, which was headed by Pacific Northwest National Lab at the Wallula Junction site, just on the other side of the Oregon-Washington state line. They ran a pilot project using supercritical CO2, which is almost entirely CO2 in its fluid/gas state at that cusp supercritical point. And again, they had a successful injection and confinement of CO2 into in that case, the Columbia River basalts at the pilot site. They injected during that pilot project 1,000 tons. It was at deeper level. The reason it's at deeper level, about 850 meters plus, is that that's the depth that you require to keep the CO2 at its supercritical point. You don't want it becoming gas too early. And so they ran that for a couple of years, both in a short-term injection followed by long-term monitoring. And we got a huge amount of data out of that project. They were able to identify the permeability structure of the Columbia River basalts and the more favorable units that we can target for CO2 injection. They're able to identify potential cap systems within the lavas, being the blocky core zones of individual lava flows. And through re-drilling and through monitoring, they were able to demonstrate that there was no vertical migration of the CO2 beyond where they had intended to inject it. And through modeling and again monitoring, they estimated that the plume, now bearing in mind this is only 1,000 tons of CO2, so it's a very small fry, didn't migrate more than about 40 meters away from the borehole. So again, a lot of information came out there, demonstrated that there is a viability for the system. There are some hang-ups. So what is this process that I've been talking about? Mineral carbonation. And it's the same in essence, regardless of whether it's in basaltic rocks, ultramafic rocks, some other types, but it involves both a dissolution and then a precipitation stage. So the first stage, you've got to dissolve something from in situ. So that's in the cases of those projects, that's dissolving the host rock. And then you need to be precipitating something. And in this case, that's precipitating one or more types of carbonate rock. In the Columbia River, it's most likely going to be calcium carbonates. In some other systems, it might be magnesium or iron carbonates. But the process has a number of different stages. If we take the example where we're taking water and CO2, that would create then a mild carbonic acid. That carbonic acid, once pumped into the subsurface, dissociates relatively rapidly into a bicarbonate ion and then carbonate and hydrogen ions. And in mafic and ultramafic rocks, those hydrogen ions will then start to react with minerals within those rocks. And particularly, they're going to start to strip out metal cations, depending on the chemistry, that could be magnesium, calcium, iron. And in doing so, then we create a material to react with the carbonate ions, and assuming we have a surface that it can precipitate onto, then we can start to generate stable carbonate minerals. As I say, that's a multi-stage process, and the conditions for that, the stages of that process, are not always that well aligned. And I've put some of the key factors here. The dissolution is favored ideally where you've got acidic fluid conditions. So that's low pH, that's the hydrogen ion. In higher temperatures, that's why it seems to work very well in Iceland, because you've got 180 degrees C at the target reservoir depth. But ideally, the dissolution generally tracks the higher the temperature, the faster the dissolution. Lower silica content, because what you're trying to do is break the silica chain with those metal cations. If you've got fewer metal cations, more silica, then there's less for it to break down. High surface area or amorphous structure. So that could be that you've got coarse crystals, or that you've got glass. Basaltic glass, for instance, will increase reactivity to some extent. And then there is a question about what pressure does to the system. It's difficult to say because pressure is usually convolved with temperature and depth, so it's not entirely clear, but generally it seems that higher CO2 pressures are favorable, and then saline water is more favorable than fresh water. The precipitation side of this doesn't track so well with dissolution, because you can't crystallize, or you can't crystallize carbonates very well in acidic conditions. It needs to be closer to base. So higher pH is favored for precipitation, and lower temperatures are also favored. If you go beyond 100 degrees, then you start to generate more clay minerals than carbonate minerals. High divalent cation content is great. That again comes from that process. Crystalline substrate helps, and saline water also helps. So some things track, some things don't. So then, following on from that, obviously, if we look at where those favorable reactivity features are within the rocks, it's going to be favored in the right-hand side of this diagram, where we have less silica. So that's your ultramafics and your mafic compositions. And those rocks also have a lot of those metal cations, particularly in the right-hand side, magnesium and iron in ultramafics. And then when we start to introduce more plagioclase, then you're introducing, at least on the right-hand end, you're introducing more calcium. So all the way through to about labradorite, you're in favorable conditions for mineral carbonation within basaltic rocks. there have been a number of studies on the reactivity rates for, say, dissolution, and the specific mineral starts to come into play, and that comes down to whether it's a silicate versus a hydrated metal cation assemblage. So the most reactive systems that you can get naturally are a mineral known as brucite, which is magnesium hydride. Doesn't have a silica chain. Next down would be olivine. So, of course, olivine is a major constituent of ultramafic rocks, unless they're highly serpentinized. And if we add water to either of those systems, then we've got the opportunity to create brucite, or in some cases, in a lot of cases, more often, serpentine, which reduces the reactivity somewhat. But still, some of the best bets for reactivity within that system. In the basaltic system, we still have that opportunity. We still have, in some cases, quite a bit of olivine, although it is then being replaced by pyroxene and feldspar. The nice thing for basalt, though, is that feldspar is more reactive than pyroxene, which is more reactive than olivine within a basaltic rock. So still a lot of potential within basaltic rocks, even though there's a lower olivine content. And then, yeah, so where does that all sit then? For subsurface injection, if we're the ones supplying the CO2 into that system, that's largely the thing that holds back the natural system, is access to CO2. If we put that CO2 into the system, then we get our highest reaction rates. We can get it with just water as well. You don't need to add CO2, but it will be a slower reaction because there isn't the building block for the carbonate in such quantity. Basalt, again, a good option, just not quite as reactive as peridotite. And that's in the subsurface. There are surface options as well. And there's a lot of talk at the moment about co-opting, whether in some critical mineral systems, which are ultramafic hosted, you're going to be grinding up rock to get critical minerals out. If you could then sparge that system, that's spraying it with water, ideally laden with CO2, or then just using natural CO2 in the atmosphere, then you've got the option, again, of sequestering or storing CO2 in a mineral form without additional energy required beyond grinding the material in the first place for critical minerals. So we have a lot of opportunity for mafic and ultramafic rocks. And to be honest, they both have great potential. The differences here are that, as I said before, the basaltic rocks are very well spread out across the state and the Pacific Northwest. So we have a lot of surface area coverage. The ultramafic rocks, again, the rocks in the orange, I didn't come up with a color scheme, so apologies for that. But ultramafic rocks, a lot less surface area, but there is also the potential for them to go to great depths. And they have very high reactivity. So again, still a great potential option. Those ultramafic rocks, I'll start with those, are emplaced in Oregon as part of the subduction system, an accretion of ocean lithosphere against the North American craton. We have two main areas to play with that surface: the Josephine ophiolite in the southwest and the Blue Mountains in the northeast. The only thing that I will mention about them is that they are, in a lot of places, already serpentinized. Now, that doesn't mean that the system won't work. It just means that it might be a bit slower in those systems. So a big part of what we need to do in the future is actually to map these out to understand where are the pristine peridotites, ultramafic rocks, versus where are the most serpentinized rocks. As I mentioned, although we have quite a few of those ultramafic rocks at the surface, they are very patchy. It's wherever they've been uplifted up to the surface. One problem for them is that a lot of them are not near economic centres or places where we're actually producing CO2. So that starts to become a problem for how do you get the CO2 to them. But interestingly, if we look at the gravity data across the state, so this is relatively low resolution, but makes a point. Those ultramafics, very dense rocks, track very nicely with where the high density, so this is Bouguer anomaly, shows where in the shallow subsurface a lot more of that material is likely to be. And there is the potential that those ultramafic systems stretch all the way through Central Oregon, a bit masked here by the Cascades, but still a potential. So a lot of opportunity in the shallow subsurface in Josephine ophiolite and the northeast of Oregon. But as I say, the lowest hanging fruit for us really is the basaltic systems, and in particular the Columbia River basalts, largely just because of the surface area coverage that we've got, and also if locally the thickness that it gets to. So there's a very substantial pile in certain parts, centered in Washington, but we also have great thickness in Oregon. The estimates that came out following the pilot study in Wallula Junction, which is the yellow star on there, we have on the order of about 40 billion tons of storage capacity within the usable parts of the Columbia River basalts. There have been other estimates that go up to about 100 billion tons, but those don't take into account the fact that you can't use a lot of that system. Yeah, you're going to be truncated in depth, but also in the usable parts of the basalts. So over the next 2 years, and this is the project that I'm primarily focused on, we're going to be studying the Columbia River basalts for the viability for carbon storage. Now, we're not injecting carbon into the subsurface. We are working out whether it is a viable system to inject CO2. So I do need to make that distinction very clear. So the things that we need to know before we can assess whether it is viable to inject would be things like the basalt thickness. So we need a minimum of 400 to 800 meters thickness. We need the right chemistry. We need to know that there is a cap rock and that cap rock has integrity, that it won't leak. We need to know what the water salinity is. The EPA has regulations for injection that you have to exceed 10,000 parts per million total dissolved solids. Basalts are very well known for having relatively clean water, so that could be a challenge in the future. We need to find if there is very dirty water within that system. So immediately we can start to hone in on where we should look within the system, but just by looking at the basalt thickness. So we can see the hotter colors here are where we've got the maximum thickness in the Columbia Basin. We can bracket based on the 400 meter contour, or we could bracket based on the 800 meter contour. So anything within those contours is a viable target. Now, as far as integrity is concerned, we don't want to be anywhere too close to an active fault or capable fault. So these faults highlighted in yellow, and this is not going to be all of them, I should point out. These are the quaternary faults. They haven't been entirely mapped in this central region, but we do know where some of them are. And then we also ideally don't want to be too close to major structures. So again, more faults, but not necessarily the quaternary faults. So we have a few target locations that we could start looking, particularly where the basalt is thickest up near the Columbia River. Incidentally, Wallula Junction pilot project on the Olympic, pretty much on the Olympic Wallula lineament, which is one of Eastern Oregon and Eastern Washington's more active structures. From that Wallula project, we have a pretty good idea of what system we're looking to characterize, and that's going to be the basaltic lavas within the Columbia River. And again, from that study, we also know relatively some of the distribution of properties of those rocks, and likely we will be targeting characterization of flow top units for the reservoir, storage system, and the entablature regions as these potential cap rocks to stop vertical ascent of CO2 if it was ever injected. In a bit more detail, there are a number of considerations in that characterization. For storage, of course, we need to know what the porosity of that material is, and the problem for basaltic rocks is that porosity is over a number of different scales. So a lot of the lavas, the flow top systems, have brecciated or rubbly flow tops, which have multiple scales of porosity, both within individual clasts, but also interclassed porosity. So a bit of a challenge to characterize that system. I have done some porosity and permeability measurement on smaller cores of basaltic rocks, and largely been on intact basaltic rocks. The right-hand image is a micro CT scan of the left-hand core of basalt. And part of the problem that you can see is that actually a lot of that porosity is not connected. So although you can get a number for porosity that might give you an indication of what the storage potential is, whether you can actually access any of that is another question. The other main type of porosity in basaltic rocks is the fracture networks. And one of the challenges that we have there is that those fracture surfaces react very rapidly with CO2-bearing fluids. So they go through a number of different stages, but as I mentioned before, two of the main products that you can end up mineralizing are either carbonates or some other assemblage, and largely those other assemblages tend to be clays. Those clays then shut off the permeability. So again, another challenge to accessing porosity through time. Don't know why that's not come up. And then going upscale from fracture networks, we can look at the much larger representation fault systems. And again, we see a lot of variability within fault systems, both in terms of their architecture, but also in their properties, depending on what stage they are. And this is just a piece of work that measured permeability for faults at various different stages, from where we have no fault through to where we have a very well-developed fault. And we see that depending on the stage that those faults were at, the amount of clay that was mineralized within them, the amount of carbonate that was mineralized within them, you can have either a permeable conduit or you can have a barrier. And it's never immediately apparent until you actually get to it and are able to measure it. So the key questions that we've got moving forward for the project really are to better understand that permeability distribution, both at the local scale, but also regionally. There have been studies using well data to map out the permeability range. From that well data, we can see that we go from very high permeabilities. These are in meters squared, so that's 10 to the minus 10 meters squared. That's more than a Darcy permeability, down to 10 to the minus 18 or 19. But about minus 20, 21, you're getting into diffusion as the only type of permeability. So it's a huge range of potential permeabilities depending on where you are within that system. We also need to understand the reactivity, so that's the mineralogy, the temperature, and there are some models for heat flow. We would want to get in situ measurements as a function of depth, but also then the fluid chemistry and distribution to understand where the dirty water is within that within those aquifers. And also there isn't a lot of subsurface stress data, so we don't actually know how easy it's going to be to fracture rocks, not to fracture rocks, how easy it is to inject into rocks without causing fracture. And largely the way that we're planning to go about that is first with a surface-based and subsurface-based characterization across the Columbia corridor. but then focusing into identifying a site that we can put a stratigraphic test well. Again, as I say, ideally somewhere where the basalt is thickest so that we can get a good characterization of the full thickness of the basalts and get that information that we would be crucial if things could move forward into a pilot study. I'm working on the technical side. I think it's very important to note that this project is not isolated in the technical aspects. We are interested to understand the perspectives of Oregonians. So we are devoting quite a lot of time to just listening to, say, the tribal nations, regional stakeholders, or nearby property owners to better understand what their perspectives would be for this. So there is a social viability condition here as well as a technical viability. And we also beginning to investigate the permitting structure for piloting or for a pilot well and then commercialization, just on the off chance that things can move forward. So might have run over time, but
Oh, great.
I shall leave it there.
Great.